So you probably tried these examples, didn't you? Problem 10A, B, C, and D. Four little cute molecules using something simple as a cyclohexene in order to make these products. And when you start at A, there's a very strong chance that you got to this question and said, well, wait a minute. This doesn't make sense. What kind of reagents can I add to this cyclohexene in order to get this? I thought that I had this in the bag. But now that I try my very first example, it seems a little bit more complicated than what it was in the beginning. So the directions are going to tell me to use cyclohexene, and there we go. And we're going to have to react something with it, and it could take more than one step. I mean, we're big boys and girls now. So long are the days long ago of just creating one reagent and saying, here you go, here's the product. We have so many reactions in our Batman tool belt of reactions in organic that we can pull from that these one-steppers kind of long gone. So they want me to start off with cyclohexene, and they want me to end up with a molecule that has an OH on it here and a ethyl group that's here. And I'm not going to worry about stereochemistry just yet. They do show me a little bit of stereochemistry. A solid wedge is on the OH, and a dashed wedge is on the CH2CH3. So what do we do? How do we go from the left-hand side to the right-hand side? And this is typically what most people do in the beginning. They look at this group and they say, oh, look, there's an OH. And here we have a double bond. Well, I know that in Orgo 1, we talked about an alkene reaction, and we said, hey, I can add something like water and acid to an alkene bond, right? And we talked about the double bond breaking. There it goes. Two sides of attachment open up here and here, and H goes on one side and OH goes onto the other. There we go. There's an OH onto a ring. Well, depending on where I put the OH, I could get it to perfectly match, but we've got a bigger problem, folks. The problem is that doing this has only added on an OH group. Now what are you going to do? And the reason I say that is because we have a CH2CH3 that we have to add on as well. So I'm digging. Batman tool belt reactions. Okay, let's see what kind of gadget I can pull out in order to get this to happen. And in Orgo 1, we talked about using the acetylide ion. And we said, hey, this is a way that we can add on to a carbon chain and make it bigger. But in order to do that, we had to have something else. And this something else was a halogen. Because this was a leaving group, pretty much, typically a bromo group. And this nucleophile came in and bam, off it goes. And it substitutes for that bromo group. I don't see a bromo group on here. Do you? No, there isn't one. So this is not going to work out for us. Well, we are in organometallics, so it probably means that they want me to use some type of organometallic reaction to make this product. And I know that we've talked about lithium, and we've talked about magnesium, and we've talked about copper now, these cuprates, lithium cuprates. Sound fancy. And those allowed me to put on things like ethyl groups, right? CH2, CH3s, as long as I put these in parentheses and add like a copper lithium, then that would put whatever was on the inside onto the ring or onto the molecule. But again, folks, we need something else in order for that to happen. You can't just take this molecule and say, here you go. We always looked for the halogen, didn't we? Seems like we always looked for that halogen, or some type of an epoxide reaction. We've been doing quite a bit of that as well. And yet I don't see either one of these here. So what looked like a simple question, what looked like it was only going to take, a minute or two to answer and pop out a question and say, here are your reagents, it's going to turn into something a little bit more complicated. And this is why I figured out the piece of the puzzle. How can I get an OH group onto the molecule as well as this ethyl group onto the molecule as well? What's the path of least resistance? The reason that I'm focused in on this is because this is an organometallic. It's a Gilman reagent, and we're in organometallic lecture. So I'm just making an assumption that they want me to use something like this in the reaction at least. Okay, so here's the R group that I need in order to make that product with. So where does that OH come from? Water and acid. It's a good choice. It does break the double bond. An H goes on one side and OH goes on to the other. That's true. I'm not saying that it's not. But is this the only way that we can get an OH onto this thing? Because the problem here is that if I do this first, then how on earth do I modify this structure now to get something like a halogen or some kind of group on it so that way it can react with an organometallic? Can't really do that easy this time around. Well, if you're clever, you might say, I know how to do this. Back in the day in Orgo 1, we talked about adding things like Br2 with water as a solvent and on a double bond. And we said the double bond breaks, two sites of attachment open up, bromine goes on one, and water goes on the other. Oh, okay. Well, that gets me a little bit closer, right? So now I've got this bromine group, and this bromine group can be substituted, and this bromine group can be substituted with whatever kind of negative alkyl group that I want to bring in. All right, so there's one option, and I'm not saying that you can't use that, but let me just do a review and relate it to some things that we've talked about already in our lecture schemes. All right, so here's the product that I need to make. That's where they want me to start. Double bond. I need an O group, and I need to add on an alkyl group. And folks, we've just talked about example after example using an epoxide. Right? I mean, it seems like that's all that we have done so far. We've talked about organometallics, but we've talked about epoxides for the most part. Can I make an epoxide with a double bond? Yes. Yes, you can. Do you remember how to do that? Maybe not. Okay, well, I can take an alkene like this, and I can add a reagent to it, and that reagent was a C double bond O OOH, and this was called a peroxy acid. This was in the grouping of the alkene reactions. It was pretty important at the time because we did bring this up and say, hey, this is a way that we can make an epoxide. And then if you go back and if you had me for Chem 251, if you rewatched any of those videos or could pull them back up, you probably would hear me say, well, it's not too important now, but wait until a little bit later. Okay, well, now's later. That's when this kind of becomes important. So if I can take a peroxy acid, and there was a common peroxy acid that we used that went under an abbreviation. I don't really care about any of that right now. MCPBA, I don't really care about that. But if you can just give me a template like this one, where R represents any old alkyl group it wants to be, doesn't matter. If we have this peroxy acid functional group, this is all that we need for this synthesis to take place. So what happens is that the double bond does break, like we said in all alkene reactions, but we end up with an epoxide that forms when that goes on. Now we're getting a little bit closer. Now we have this epoxide. This epoxide is something that we've used time and time again in these past example problems. And I know that these epoxides are very reactive. And I know that at this point, if I go in and add another reagent, and in this case, what else do you need to add on? I see the oxygen that will probably form my OH group sooner or later. Oh, okay, I see. The epoxide's going to open up. That epoxide oxygen is going to be the oxygen up here for the OH group that I'm after. So that kind of takes care of itself. The only thing now that I need to worry with is this CH3CH2 group. So if I can bring that in using a lithium cuprate or a Gilman reagent, then this molecule will boink, open up that ring, and goes onto one side, and my CH2CH3 goes onto the other side. This is a full-blown negative at this point. So now what I need to do is add some type of proton, and this proton could come in the form of HCl if you want to be proper. So I could add HCl there, and that will protonate the O group, and that will give me what I'm after. All right, now, I know what you're thinking. Some of you are going to look at this group and say, well, wait a minute, this product has the OH pointed up, but down here, down below, this OH group is going to be pointed up and to the right. So that's not really the same product. Yes, it is. It's the same thing because I just have to turn this molecule. That's all that I have to do. So the OH group and the ethyl group are still side by side. And that's what you see down here. This OH, what will be OH, and the CH2CH3 group, they are side by side on a ring with nothing else on the ring. So they are identical compounds. If you name them, it would be an identical compound. So let's go through and name it. All right. So here I have a cyclohexane ring. So cyclohexane. But I know it's not an ane because there's an alcohol group. And that gets an ending of OL, so cyclohexanol. Well, because I give priority to the OH group, because I've named it as an alcohol, it gets priority, this automatically is the number 1 carbon. So on the number 2 carbon, which is right beside of it, I have an ethyl group. So this is a 2-ethyl cyclohexanol. There's the name for that alcohol that I've made. So let's talk organic. Let's use our words. I've started with cyclohexene. I've taken cyclohexene and I've reacted it with a peroxy acid such as MCPBA. This peroxy acid will attack the double bond, and those sp2 carbons of the double bond will be destroyed, and that double bond will form an epoxide unit. That epoxide unit will then react with a Gilman reagent. That Gilman reagent will then supply the needed alkyl group in the form of a nucleophile to break open the epoxide ring, forming a negative oxygen and an alkylated ring at this point. That negative oxygen will now be protonated through the use of hydrochloric acid, and that hydrogen will satisfy that negative on the oxygen to form an alcohol. So I have taken cyclohexene and I have produced 2-methyl cyclohexanol in that synthesis route. Whew! Again, a mouthful, but look at what you're learning. That's the take-home message here, right? Before this, could you have followed this through? Before this, if I kind of just blatantly just came out and said, this is how you do a Gilman and this is what it means, could you actually follow through with me and understand what was going on? Now, you might be thinking, I still didn't understand you, but I think you're getting closer. And there's 3 more examples. So we're going to be able to test our stuff 3 more times in order to feel more comfortable with the multi-synthesis route here. All right, so this took me 15 minutes to talk about 1 reaction scheme, 1 synthesis route, and we've got 3 more to do. But the other 3 aren't going to take as long. All right, so They want me to start off with cyclohexene, and they want me to bring up something, and they want me to end up with a ring that still has a double bond somewhere, and off of one of those carbons, I have a CH2, CH3. Oh, let's think about this. I started with a double bond, but my product has a double bond. So whatever I do to it in the first step, I'm probably going to have to target this double bond piece. There's nothing else on here that I can react with, right? There's no bromo groups. There's nothing. So I'm going to be forced to break that double bond. But when I break it, look at my product. It's got to reform. Somehow. It has to come back. Well, how can we do that? How can we reform double bonds? The only way that we've talked about how to do this and make double bonds in products is through the use of an elimination. Oh, no. All of those organic ones are going to be coming back, especially that substitution and elimination chapter, which are two of the most important chapters of the whole semester, and that happens at the very end of the semester when final exams and crunch time happens. And we expect and assume that you still know those. That's the thing here. That's what makes organic a little rough, especially Orgo 2. All right, so let's just kind of go with the flow here. Let's do what we did in the very first example. Let's add on a peroxy acid. So there's my random peroxy acid. It doesn't really matter which one it is. And this will break open the double bond, and an epoxide ring will form because of that. Now what to do with it? Well, if I take a look at this structure, again, I need to add on an alkyl group, so why not do it? I mean, I need to do it now. So it seems like this would be a pretty good time to do this, just like we did in the previous example problem, right? I'll just add on CH3, CH2, two of them, and copper and lithium. So I'll add my Gilman reagent, just like in example A. And what happens is that the epoxide now will break open, and that epoxide will free up that oxygen, and it frees up another spot on that other carbon, right? That love triangle got broken. Oh gosh, boo-hoo. They can find somebody else. There we are. This is where we ended up. And normally at this point, like what we did before, at this point, we can now add HCl, and we get this ring. It has an OH group on it, and a CH2, CH3 group on it. But that's not what I'm after. Look at that. I'm not after that. I'm close, but I need to get rid of the OH group, and I need to form a double bond. Oh. Well, in the last lecture module, didn't we talk about that? Do you remember that? Can you connect the pieces? What is that called? We did a lab on it, folks. I need to remove an OH group and prevent something from coming onto it. That is an elimination. If I can remove the OH group, well, I need a double bond to form, and that could be the removal of a hydrogen as well. This is a dehydration of an alcohol. That's what this is. Do you remember how to dehydrate an alcohol? I hope so, because we just did it in the first lecture module. And we added something like sulfuric acid, H2SO4, with a little bit of heat. So we protonate the OH group. That OH group now leaves because it turns into a very good leaving group. And behind leaves a double bond because nothing is going to go on in its place. So this has formed now the ring with the double bond, and that double bond is on a carbon that now has an alkyl group. Always keep in mind, when dehydration happens, we make sure that this double bond will form using the most substituted carbons that we can get. So by default, it will move, the double bond will form to the end of the carbon that has the ethyl group on it. Oh gosh, now let's do a summary. I take cyclohexene, I react it with a peroxy acid to generate an epoxide. This epoxide ring stability is very unstable, very reactive, so I've added a Gilman reagent that brings an ethyl group to the ring. So the epoxide opens up, the ethyl group is attached, and that frees up an oxygen that will become protonated to make an alcohol group. That alcohol group now is going to undergo an elimination reaction through the process of a dehydration of an alcohol, and that requires sulfuric acid and some heat. So when the OH group leaves, the more substituted product is formed, and that double bond will gravitate toward the carbon that has the ethyl group on it as well. Folks, that's the synthesis part for B. Again, very wordy, but that's good. We're using the words that we're learning throughout the organic course. Now, let's take a look at C. Again, cyclohexene, and we want to end up this time with a cyclohexene, a CH3, with a Br on that same carbon. Okay. How we do this? Let's kind of go with the flow. Let's kind of mimic what we did in A and B, and then we're going to have to modify maybe. Who knows? But, you know, if we get to a stopping point and we realize that something's not going to work, that's perfectly fine. That's what erasers are for. So we'll figure it out as we go. So let's use a peroxy acid, and we'll break open that double bond, and we will form an epoxide on the ring. There we go. That's what we did in the first two, so we'll do it here. So it looks like we have to add on an alkyl group, and this alkyl group is going to be a CH3 group this time, not a CH3-CH2 group. So it's a different Gilman, but maybe I can still use a Gilman, right? I mean, this is not going to be a problem. So if I need this epoxide to open up, I could use a CH3, two of those, with my copper and lithium. There's my Gilman. That opens up this epoxide ring. So my O goes here, and my CH3 goes there. So this is a pretty surefire way of at least getting up to this point. And then you know probably what's next is acid. So this is going to donate a proton. So there's my CH3, and here's my OH group. All right, so nothing that we've done so far has been surprising for part C, right? Nothing. All of this we kind of did in A, we did it in B, and we're doing it here. So now I've got to figure out, this is what I have at this point. I need the OH to go away. And it looks like I need to add a bromine onto it. All right, well, we just talked about how to get an OH to go away. We talked about dehydration just now, didn't we? So let's do it again. So I'm going to add sulfuric acid here with some heat. And this is going to form a ring structure. And that OH boop, is going to go away. And a double bond is going to form to give me the more substituted product. So this is what we would end up with here. So this is maybe giving me a little bit closer. I've gotten rid of the OH group. I don't see that in the product. I needed to get rid of it. That's the way that we can get rid of one. And now I've formed this double bond yet again. But now that product does not have a double bond, does it? No, it does not. This product also has a bromine, and I don't really have one here yet. Do you remember how to add on a bromine, just one, to a double bond? I mean, we're really digging now. We are digging in the very early stages of Orgo 1. But I hope that you remembered it. Because all this requires is HBr. Huh? Yeah, that's all that it was. It was a double bond. Remember, I'm going to draw it here in the center. So I'm going to start off with this. And we added HBr. So the way that reaction worked is that we targeted the double bond. That was my negative area. And there it goes. It breaks. Two sides of attachment open up here and here. That's where my double bond carbons were. So H goes on one side, Br goes on to the other, and this was a Markovnikov reaction where hydrogens play with other little hydrogens. Remember, they're very snooty. When hydrogens go out onto the playground, they're going to find other little hydrogens to play with and only hang out with those little hydrogens, and that's all. So out of these two carbons, which one has more hydrogen? It's going to be the one on the top, the way that I've drawn it here. So hydrogen is going to add on there. Ew, that's the hydrogen. And then the bromine will come on next. And folks, this gives me what I'm after. This allowed a more stable carbocation to form. That's why we did that. When this double bond breaks, two sides of attachment open up, one on top and one on bottom. This one on the bottom is a tertiary carbocation because it's attached to three other carbons. That is more stable. Therefore, when the negative bromine comes into the picture, it's going to attack that more stable positive carbocation. And that is why the bromine goes to that carbon every single time. All right, let's use our words. Let's do a recap. I know you hate when I say that. I know. Use your words. I'm like your mama, right? Okay. Cyclohexene has reacted with the peroxy acid to make an epoxide. The epoxide has significant strain. That epoxide will react very easily, and it will react with a Gilman's reagent. That Gilman's reagent will alkylate the chain or the ring, and that will put on a methyl group. We're then going to add hydrochloric acid to protonate the oxygen. We need to eliminate the alcohol group through a dehydration reaction to form a double bond, an alkene, that is more substituted. That double bond is then going to react with hydrobromic acid, and a Markovnikov reaction goes forward, breaking the double bond, two sides of attachment open up, creating a tertiary carbocation that bromine will be attached to. Whoa. Who signed me up for this class? Is that what you're thinking? Okay, we'll just wait, because let's look at the product for D. There you go. Now you can ask that question. Who signed me up for this class? I did not sign up to take this. How is this even relevant? I know what's going through your head. I was there too. So here's D. This is the product that we need. And we need to make this from cyclohexene. Yeah, we can do that. We can do that. We're organic chemists now. We can do this. We just need to pick out the correct pathway and reagents, and we got it. Okay, well, let's do what we did before. We're going to take this cyclohexene, and we're going to add this double bond OOH peroxy acid stuff, and this forms an epoxide, which is very reactive, so I know it's going to go forward, which is why we do it. So it looks like I'm elongating the chain. Well, what are we elongating? We're adding this whole piece up here, right? Okay, well, that's not a problem. The Gilmans will be able to do that for me. The only thing I have to do is say, hey, look, I'm going to add this benzene ring on. And there we go. And off of this benzene ring, I've got this copper and lithium stuff. It's kind of how we draw that. We like to draw it that way to let you know that copper lithium is attached. It is a Gilman's, and it's attached directly to that benzene ring. All right, so when that happens, the epoxide is going to go off, and we see boing, an OH that comes up here. And then off of this, we also see this benzene ring. All right, so I'm going to draw the benzene ring on here, and there it is. I'm getting closer. I'm getting closer. Look at that. Well, at this point, I'm probably going to add hydrochloric, And this gives me this bottom ring. There we go. Has an OH group on it right there. And then off of this ring, I also get another ring because that's what my Gilman just added. So if I can get rid of that OH, I'm going to be good. So how do I get rid of the OH? Oh, well, we just talked about it, right? We can just do this H2SO4 that we learned back in the day a couple of weeks ago. We can eliminate this group. And when we eliminate the group, what we will end up with is a ring structure that has a double bond. And that double bond carbon is also connected to this benzene. But I'm not quite there. Why not? Because I've got the freaking double bond that needs to go away. So how can we get rid of this double bond? Pretty simple. If you need to break a double bond and you don't need any other groups attached to it, folks, that was one of those Batman reaction days. That's H2 and platinum. H2 and platinum. You could use H2 and Linlar too. I don't care. Does the same thing. So my double bond will break. Two sites of attachment open up, top and bottom, and they go hydrogen on the top and hydrogen on the bottom. And that forms my product. So peroxy acid, my Gilman, acidify it, eliminate it, and then H2 platinum it to break the double bond, and I have the product that I need. There's your examples. A, B, C, D,